Hello, I'm Pierre Paulin. I'm Director of R&D, responsible for the embedded vision processors at Synopsys, where I've been working for the last 6 or 7 years. Prior to that, I was with ST Microelectronics, working both in Europe and in North America. Today, I'll be talking about trends in embedded vision and AI in edge-based applications. There'll be three main topics. First, the trends in machine learning for edge applications. And from that, what are the key challenges and opportunities? And among the challenges, we'll focus mostly on bandwidth optimization. In the last years, we've seen the emergence of AI-based techniques for embedded systems, both in image and in audio. In the image and video field, we see the appearance of initially classification, such as detecting a car in an image, or detection, where we detect instances of specific cars and draw a boundary, or more complex scene segmentation, where the images is labeled very accurately. This is used in surveillance, augmented reality, virtual reality, and clearly in automotive. We also see use for image quality improvement, like super resolution or denoising, computational photography, multifunction printers, digital TV. And we show here a small example where we have a very pixelated image and with a advanced super resolution generating a higher resolution image, even when there's very little information available. Most of these technologies are based on convolution neural networks, or CNN, used in image processing. In parallel with this development in the last 5-6 years, we've also seen significant advances in audio and natural language processing. So in the speech and text processing, we saw the appearance of recurrent neural networks, then 1D convolutions, and most recently, the class of graphs called transformers. We also see use for audio scene classification, where you're listening to an audio environment and detecting what environment it is, like a shopping center, a soccer field, or other environments. And these have mostly used convolution LSTMs. Let's dive deeper now into each of these categories. In the field of image and vision, the first technology to appear was for classification, where you take an image and recognize that it's a street. And one of the first groundbreaking technologies and graphs was AlexNet at the University of Toronto. And this was developed in 2012, followed with higher accuracy graphs like VGG and ResNet in 2014 and 15, and the most recent and more compact graphs called MobileNet V1, V2, up to 2018. In the 2014 period, we saw the appearance of object detection, where we're not only recognizing a car, but drawing a boundary around the car or defining the segmentation of a specific instance. Some of the well-known graphs include YOLO V2, MaskRCNN, and the more recent YOLO V3 in 2019. A more complex technology is called scene segmentation, where in addition to recognizing classes of objects, we're actually labeling each of the pixels of that class of objects. So in this case, we have the blue pixels, which are the precise contours of the cars in the image, and the red pixels, which represent pedestrians. And well-known graphs include SegNet, DeepLab, and more recently, DSNet. And the most recent and more sophisticated technology is a category called panoptic vision, or panoptic scene segmentation, where in addition to scene segmentation, we're also identifying the specific instances. So in this case, we have 4 cars identified, or three cars and a part of a car in 4 different colors, as well as each of the instances of the pedestrians are also identified with different colors. And DeepLab is one of the recent examples of this technology. This continues to evolve and continue to evolve quickly. In 2020, we saw the appearance of a new category of graphs called EfficientNet. And from that, which is a classification graph, and from that, we see derivatives such as EfficientDet to do efficient detection, object detection, using the base classification graph EfficientNet. And we also have the panoptic segmentation variant of EfficientNet called EfficientPS. Another well-known family is MobileNet v3, appearing in 2020, and YOLO v4. Synopsys has been involved since early 2014 on the development of dedicated accelerators, and our first generation came out in mid-2015. We then developed a second generation, much more aggressive second generation in 2017. Our third generation last 2 years ago, and our fourth generation was early this year, and we're already introducing our fifth generation by the end of the year, and our sixth generation next year. And this is this 6-year experience has allowed us to track some of these key trends, and I'm going to share some of those with you today. So the first important observation is that the increased accuracy comes at a cost. Let's look at some of the progress we see in red. These are conventional computer vision algorithms and shallow learning applications. And in 2010 to 2012, you can see those red dots go from about 20% accuracy all the way up to about 75% accuracy. And 2012 was the appearance of the famous AlexNet, and where over 80% accuracy was achieved. And for the first time, an AI-based approach was exceeding the best results of the more conventional approaches. The other key milestone was in 2015, where the best results were achieving results that were above those of a human being, at close to 96, 97%. That has continued. Of course, there's a cost to this, and you can see back in 2016, the VGG16 is about close to 1,000 pixels per operation. We've seen that improve with the inception of ResNet and MobileNets, but still at over between 10 and 100 operations per pixel to achieve a given accuracy. So let's take a closer look at these graphs and their compute requirements. So we have on the x-axis the number of million multiplications for a given accuracy on the y-axis. So we have AlexNet in the orange bubble at about 55% accuracy and requiring about 1 million multiplications. About 2 years later, in 2014, we saw the appearance of VGG16, much better accuracy. We're at over 70%, but at much higher computation cost. So what we'd like to see, of course, is the reduction of the computation costs and the increase of accuracy. And the most recent efforts in 2016 with Inception family, and there's a V1 to V4, and this is shown as a curve here, gives a set of trade-offs between accuracy and compute requirements. We also see ResNet in green, which follows a similar trend. In 2018, we saw the appearance of the MobileNet family, MobileNet V2 in MobileNet V1 in purple, and MobileNet V2 in brown, and the DenseNet in gray, showing a significant reduction in compute requirements. Again, these are families, so the curves like MobileNet V1 has a series of implementations that have different accuracy versus computation costs. And finally, in 2019, we have the latest generation in green is the EfficientNet family, and this is a range of graphs from EfficientNet B0 to B7. And then the other more recent family is MobileNet V3 in black, showing another trade-off in compute accuracy, lower compute accuracy, and lower compute requirement, but also lower accuracy. So these two represent kind of the state of the art today in these trade-offs between compute requirements and detection accuracy, classification accuracy. And over that period between The original VG16 in 2014 and the latest MobileNet v3 for the same accuracy, we see about a 300 times reduction of computation requirements. The second trend is a reduction in model sizes. So this new chart shows on the x-axis the number of million weights, and the y-axis is, as in the previous slide, is the accuracy. So here we have AlexNet, which requires about 60 million weights for a 55% accuracy. VG16 in 2014 increased the accuracy significantly, but the weight went from 60 million to over 100 million. Again, what we'd like to see is a trend towards better accuracy and smaller model sizes. And that's what happened with both Inception family and the ResNet family in blue and green. In 2018, we saw MobileNet v1, DenseNet, and MobileNet v2 in purple, brown, and gray, and showing you a further reduction in model size and a trade-off in accuracy. And more recently, the latest EfficientNet and MobileNet families in green and black, showing, and particularly see with EfficientNet, a significant increase in accuracy and a continued reduction in model size. So in this case, between the VG16 in 2014 and 5 years later, with either MobileNet or EfficientNet, we see about a 50x reduction in model size. The third trend is the reduced data reuse and parallelism. These new graphs, in particular the MobileNet and EfficientNet graphs, make use of a thing called depthwise separable kernels. And in contrast with the traditional one-by-one convolution as shown here, the depthwise separable have different data flow. While the traditional convolution on the top has extremely high computation as a negative, but as a positive, there's a lot of data reuse. You can see the data computed in the first layer is shared by multiple layers in the second set of layers. So that's high data reuse and also easy to exploit parallelism. So those are the positives. The depthwise separable shown on the bottom has lower computation, which is a very strong positive. We saw this 300x reduction, but that does come at a cost. And you can see here that there's much less data sharing, that the first set of layers passes on only a single data to the next layer, and it's not broadcast to multiple layers. So there's less data reuse, and the parallelism is also harder to exploit. A fourth trend is that the increasing dominance of feature map bandwidth. So we'll take an example here of a DenseNet. In most of the graphs before DenseNet, the 2014-15 graphs like ResNet and Inception graphs, mostly have a set of layers that feed data, which is the feature map, the intermediate values, are fed to the next layer, and so on. And there's not a lot of a long lifetime of the feature map, as is shown in the graph at the top. However, if we look into the dense block number 1, 2, and 3, and we zoom in on that functionality, we see that inside that part of the graph, in fact, the pink layers at the lower left-hand side feed data through the red arrows to multiple layers, the green, the purple, the yellow, and the orange. And these red arrows represent the intermediate computations, which we call the feature maps. So these are intermediate results between layers. And the lifetime is very long. And the same thing happens from the green layers, and they send data to the next purple, yellow, and orange layers. So it means these long lifetimes implies high bandwidth to store these feature maps. So to summarize, two very positive trends: reduced computational requirements. We saw a 300x reduction between 2014 and 19. A reduced model size, again, a 50x reduction in this case in model sizes in those same 5 years. Does come at a cost, some reduced data reuse and parallelism because of the depthwise separable convolutions using MobileNet and EfficientNet families. And the fourth trend is that the feature map bandwidth becomes dominant as experienced in the DenseNet. So that focus was on imaging and video. Let's take a look at other domains like audio and speech. In the 2014 period, we saw the emergence of a class of graphs called RNN, recurrent neural networks, with examples like LSTM and GRU, and a well-known graph called Sec2Sec. And about 4 years ago, we saw these RNNs being increasingly replaced by 1D convolutions, and a representative of that is WaveNet. And even more recently, we have a class of graphs called transformers. And we'll look into the next slide at some of the performance results of a graph, transformer graph. The key trend here is that each of these families has more data reuse and is easier to parallelize and also easier to train, which is an important component of this equation. So let's take a closer look at these latest transformers. Here we have on the right-hand side a set of results. The x-axis is time, and the bars represent different graphs that were implemented in the 2018 to 2020 period. The y-axis is the accuracy for a challenge called RACE. This is a SAT-like, a Scholastic Aptitude Testing-like reading comprehension, where the system is given a text and then a set of questions is asked about that text. Now, the best result for a human being is 94.5% accuracy. However, the average result for most human beings is about 75%. So the 95 is kind of the smartest person that took this test. And we see a series of results. The 1D convolutions in 2018 achieved an accuracy of about 50%. And then we saw in the mid-2019 graphs like BERT-Large or XLNet achieving results that are equal or better than the human average, which is about 75%. And then we see that in 2020, the latest Megatron is starting to get pretty close to the smartest human that took this test at 90%. So what are some of the key opportunities and challenges that come out of these trends? Well, the first opportunity is a drive towards more efficient networks that are really focused on real-world constraints. A lot of the work in 2012 to 2016 was really focused on winning competitions, and it was an academic work primarily. But between 2016 and 2020, we saw the appearance of much more compact graphs that operate on real resolution images and real world constraints. So that's the first opportunity. Another huge opportunity is that this is a whole new field, which in fact is supported by a single well-defined abstract high-level representation, this neural network graph. And better still, we have de facto only 2 de facto standards to capture this data representation, this high-level representation. The well-known TensorFlow and the ONNX, the Open Neural Network Exchange format, which basically these 2 are the dominants used in the world today. Before that, it was Caffe was one of the main ones. So this has never happened in 60 years of computer science, where a wide field of applications is covered by a single abstraction and only 2 programming representations. As you know, we've had hundreds of different programming languages covering a wide range of fields between the 50s and the 2020s. So, of course, with these opportunities comes some big challenges. First one is to optimize the compute resource utilization under very tight bandwidth constraints. It's quite easy to create a lot of maps and instantiate them. What's much harder is to do this under tight bandwidth constraints, because the memory bandwidth is not scaling with the compute resources. The other challenge is to optimize the energy efficiency as expressed in millijoules per frame. And that energy efficiency typically is related to resource utilization. That is, if you can get high MAC resource utilization, you can get higher efficiency. And also make use of memory bandwidth. And memory bandwidth has a very direct impact on MAC utilization, because you can be starved for data if you don't have enough bandwidth. And also memory bandwidth costs energy, because typically half of the energy of an SoC is in the DRAM interface. The second big challenge is to achieve extremely low power and low area while still keeping high flexibility. The high flexibility is absolutely needed to adapt to the constant change and innovation of neural network-based applications. And you saw in the last 6 years how much progress has been made between 2014 and 2020. But we still need the low power and low area. We initially started with this whole field was accelerated by the appearance of high performance computing environments and general purpose GPUs. But these came with a high cost and high power. So we still need to be able to reduce the power and area by creating more domain-specific compute platforms. And finally, with the wonderful opportunity of this high-level standard representation that can be captured in TensorFlow frameworks or ONNX representations, this still means that we're mapping this very high-level abstract description onto a very complex, parallel, heterogeneous compute platform. And the complexity of the neural network compiler tools is extremely high. And this is the single biggest investment in the embedded vision processor program that I'm responsible for in terms of project resources. Nevertheless, it is a high investment, but we have been able to achieve very high performance mapping and high resource utilization. But it is a very expensive investment. So of these challenges, for the rest of the presentation, I'll focus mostly on the compute resource utilization under tight bandwidth constraints. So the issue, put simply, is that if we take a unoptimized 1000 MAC processing unit, we'll get 2 teraops, but we'll very quickly exceed the capability of an LPDDR4 or 5 as we scale beyond this 2 teraops peak, as you implement more of these 1000 MAC PUs to achieve higher performance. So the challenge here is about reducing the bandwidth requirements, which need to be closer to these real-world constraints of an LPDDR interface. So this bandwidth optimization is the single most important challenge. And it's important because bandwidth reduction has a direct impact on performance, because you will be data starved if you cannot make use of the LPDDR bandwidth. And also has a direct impact on power, because in typical implementations, up to 50% of the SOC power is in fact in the DRAM axis. So how do we flatten the curve? So let's take a look at a first level bandwidth reduction technique, and this is at the architectural level. So I took here the example of our internal DNN engine, and this sort of shows a very simple representation of that engine that has AXI interfaces, synchronizations, and DMAs. And inside has 2 processing elements, one specialized towards 2D convolutions, which is the dominant computation, and a second specialized towards the fully connected layer to do classification. And this has a 1D data path. Key thing here is that we've created a kind of a dedicated domain-specific architecture and a dedicated memory architecture to support data locality to reduce external memory bandwidth. So we do not have a general purpose memory architecture here. We really designed a domain-specific dual architecture with a multi-bank wide memory for feature maps and a different very wide multi-bank memory for coefficients. We also have accumulator memories inside the convolution engines. And this is the first type of technique, along with the scheduling techniques, to schedule data to keep it very inside the L1 memories. A second class of data optimization or bandwidth optimization is through data compression. A simple form of data compression is through coefficient pruning. This is done offline. That's where you examine a graph and look at coefficients with near 0 values. And then you zero those values and do a graph retraining to recover the accuracy. And In modern graphs, typically you can reduce the coefficients bandwidth by about 60%. That is, we can make about 60% of the coefficients zeroed out and then recover the accuracy through graph retraining. Then once that graph has been pruned, we then store the coefficients in the WM SRAM on the right-hand side, which stores the weight memories. And those are stored in compressed format, and they're decompressed inside the DNN engine, directly inside the registers. So that reduces the WM memory size. The second class of compression is a runtime compression. The first one was a static compression done offline. The second one is a dynamic compression. And this is a compression and decompression because the feature maps are calculated at runtime, and this is not known at compile time. So this technology is hardware supported. We use a simplified version of a Huffman encoding that's done in hardware. It's implemented inside our DMA. And with this technology, we're able to reduce bandwidth by about 40% through this runtime compression decompression. So this helps flatten the curve, and we use these technologies in our second and third generation DNN engines in the 2016 to 17 period. But we need to go further. So let's look at a more aggressive type of optimizations. We call these advanced data bandwidth reduction techniques. And more specifically, this is a form of multi-level layer fusion and multi-level tiling. But let's look at this one step at a time. First, we have at the bottom a simple diagram showing we have a series of parallel accelerators, PU1 to PUN, that operate from local L1 memory, closely coupled with the accelerator. We have an on-chip shared L memory, typically a few megabyte, and an off-chip memory in red, DDR-L3. So on the top of the diagram, we have a simple snippet of a graph with a half dozen layers. These are in fact a small subset of the MobileNet graph that have convolution 1 by 1 and convolution 3 by depth-wise 3 by 3 convolutions. So inside those white boxes, we have a set of merge layers. So those are executed in a merge fashion. And we can go, and the data that is computed can be large feature maps. And because they can be quite large, they will need to be stored off chip into the red DDR. So those red arrows represent storage into the L3 DDR. We would like to reduce that bandwidth. So what we do, we can merge layers into layer groups. So in this case, we've merged the first 4 layers into a single group. And by doing that, and by analyzing the data dependencies and the data sizes, we can actually store those red arrows now become green arrows because the green arrow represents data that is stored in the L1 memory, the local closely coupled memory inside the engine. So all those green arrows are now local bandwidth and do not appear as red bandwidth on the DDR-L3. So you can still see, however, that some of the feature maps are too large to store in L1, and therefore they need to be stored in L3. So there are half dozen red arrows that still go to L3. But we've improved bandwidth quite a bit. But let's go further. And the way we go further is we take those layer groups, which were the green boxes, we now fuse them into segments in the blue boxes. Now, inside those segments, you still have the red arrows, and the red arrows were red because they're too large. The feature maps are too large to fit into L3. So simply by fusing them to segments does not solve the issue. What we need to do is that we need to tile these large feature maps into small tiles, and each of those small tiles can fit inside the L2 memory. So we need to dimension the L2 memory in a way that those red arrows become blue arrows, and they are stored in the L2 memory. And as I said, for typical graphs, it's a couple to 8 megabyte is typically the range we see to achieve this efficiently. So if we look at the end result of this, if we combine these technologies, the feature map compression, the coefficients, the multi-level layer fusion, the multi-level tiling in red, we see that this final red curve shows that we're able to scale the performance of a full HD MobileNet V1 and still fit within the constraints of an LPDDR4 or an LPDDR5, as shown on the chart on the right-hand side. So a significant flattening of the curve at the expense of some complex tools and some hardware support. So to summarize, we've seen 4 main trends in the AI neural networks, 2 positive ones: reduced computational requirements up to 300x in 5 years, reduced model sizes, we've seen 50x in 5 years, at the cost of reduced data reuse and parallelism because of the introduction and use of depthwise separable convolutions in EfficientNet and MobileNet and YOLO v4. And a 4th trend is that the feature map bandwidth is becoming more dominant through the use of longer lifetimes for feature maps. And so the challenge is that we need to optimize compute resource utilization under tight bandwidth constraints, because the ratio of compute and bandwidth is changing, and bandwidth is rising, and compute requirements are going up, and memory interfaces are not scaling to the same level. So some of the solutions presented here are static coefficient pruning and dynamic data compression that are implemented in the architecture and supporting tools. And even more important is the combination of multi-level layer merging, layer fusion into groups, and multi-level tiling to store into L2 memory. And all this is supporting in complex mapping tools. Thank you. I'll be taking a few questions. Let's see. First question I receive is a question on the graphs that we've used. So which graphs are the most used by our customers in our experience? And are these graphs mostly standard graphs, or are they custom graphs? I think we've received over 200 graphs in the last 3-4 years. So a wide diversity of graphs and a wide class of applications, as diverse as the customers themselves. What we see usually in the first phase is a set of rather old graphs for benchmarking purposes. And we see graphs like ResNet 50, YOLO v2, MobileNet v1. And they're usually using low resolution. And the reason they do that is to do apples to apples comparison between different technologies. More recently, in the last year, we've seen a little bit of MobileNet v2 and even more recently v3, YOLO v3, and the new EfficientNet variants are starting to appear. I would say probably 2/3 of the graphs we receive are standard graphs, and about 1/3 of the graphs we receive in those 200 are custom graphs. But even for those custom graphs, most of those customers are differentiating, but they usually don't start from scratch, especially in vision and audio. We do see graphs from scratch in radar and LiDAR a little bit, but mostly in vision and audio, we see standard graphs, but then they do fine tuning of those standard graphs, and they tune to their application domain, to the characteristics of their application, which can be video surveillance or automotive, very different characteristics and throughput, and also very different resolutions. So that's a quick answer to which graphs are used and are they standard or custom. Second question is, what are the biggest pitfalls when benchmarking graphs on embedded processors for these machine learning and AI applications? I think the biggest pitfall is that people start with these standard graphs. They're well known, they're usually older, they're usually low resolution. You know, they'll use patch sizes of typically 224 by 224. The most common graph we get for benchmarking is ResNet 50. So that's great for doing comparisons and competitive analysis, but it's also not great because it really is, you're comparing apples and apples, but the product is cucumbers or pumpkins. So you're usually running either HD, full HD, or even 4K, 8K. So these academic examples are not at all representative. And most people are not running ResNet 50. They expect to run the more modern graphs, which have just come out in the last 6 months. So you really need to be able to ask whoever you're evaluating to be able to run these latest graphs and run them at full resolution. And so I would say focus on modern graphs, focus on high resolution, or whatever resolution you're using in your real application. And also don't run just standard graphs. Make sure you put in some, you test the hardware you're evaluating, use some custom graphs that you may have access to or developed yourself. Last question that I have time for, I think, what are the biggest obstacles to high macularization? That is a really important question. As I mentioned, I think the first obstacle is bandwidth and how much and how well you use bandwidth. These bandwidth limitations come from the real world. We cannot scale. We're scaling performance, from 1 teraop to hundreds of teraops in automotive applications, but we don't have access to the same bandwidth that would be required to support that. So you need to be very efficient with bandwidth. And that usually means that your resources are starved for bandwidth. So that's the first obstacle. The second obstacle is, the evolution of the, as I mentioned in the first part of the presentation, evolution of the technology itself and the use of depth-wise separable, which have lower data reuse and harder to parallelize. So these increase the bandwidth to computation ratio and it makes it harder. So again, it comes down to efficient use of bandwidth. So I'm going to have to stop here. Thank you for these questions. And I look forward to meeting many of you in the real world in the near future. Thank you.